Good morning, everyone. I would like to welcome you to the opening ceremony of the new Center for Terahertz Science and Technology in Eindhoven. I am Chigo Okonkwo, and I'm an associate professor at the Electro-Optical Communications group at Electrical Engineering, and I will be your master of ceremony for today. So we're very glad to launch this center, as this will be the very first center focused on terahertz science and technology in the Netherlands and Benelux. During this ceremony, we will hear the objectives of the center from the founding team, and we'll get an overview of terahertz activities in the Netherlands by different research groups and industry. But before that, to officially start today's ceremony, I would like to invite our TU president, Robert Jan Smit, to give an overview and provide some focus to this ceremony. Please. The floor is yours.
Yeah. Super eyes. That is what comes to mind when reading about the amazing applications of terahertz technology. Terahertz technology gives humans super eyes, which allows us to see things which are otherwise hidden. And now, researchers here in Eindhoven are joining forces in the CTSTe to advance terahertz technology, to make it accessible to a much larger group of users, and to make it accessible to the world. If I have to sum this all up in one headline, I would say the following: New Eindhoven Research Center gives the world super eyes. It is needless to say that I'm proud of this initiative, which, by the way, fits perfectly well within the theme of our 65th anniversary, Heroes Like You. The promise of terahertz technology is almost unbelievable. The range of existing and potential applications of terahertz technology is just amazing. It can be used to detect cancer, to detect carriers, to find contraband, or to find concealed weapons, to see the composition of materials, to inspect the quality of medications and food, to create astronomical telescopes. And I'm sure that the researchers which are present here today have many more astonishing applications in mind. I'm proud that our university excels in a range of areas contributing to this very important enabling technology. And I'm even more proud that one of the key ambitions of the Center for Terahertz Science and Technology Eindhoven is to democratize the access to terahertz technology. The aim of the center is to strongly reduce both the size and the costs of terahertz technology, making it as such beneficial and applicable to a larger group of users. Since cooperation is in the DNA of our university, it comes to me as no surprise to see that the work at the TU on terahertz has been and will be performed in cooperation with a large network of partners. The CTSTe will work together with a range of renowned research institutes. And, very important, there is solid cooperation with industry. And therefore, I'm happy to see that at this launch events, there are both representatives and speakers from research institutes and from industry. And not just industry from our impressive Brainport region. And therefore, I wish everyone involved in this impressive new center and this impressive new initiative, and especially the founding professors, lots of success. And there I would like to mention in particular Marion Matters-Kammerer, Jaime Gomez-Rivas, Ildefonso Tavour Monroy, and of course Doak van Mechelen. I'm very much looking forward to the result of your work and to the super eyes you're going to be creating. Thank you very much for your attention. Have a great day.
Thank you very much. So next, I would like to introduce Mr. Onno Hauskamp. So Onno is Chief Technology and Innovation Cooperation Advisor at the province of Noord-Brabant. He has been responsible for putting terahertz technologies as a key emerging technology in the agenda of the province. He will now take some actions together with the TUE president in the opening of the new center.
Thank you, Chigo. Terahertz technology. Me not having a technical background, I can actually only wonder what if this wonderful new technology will make possible for consumers and industry. But I guess we'll find out. For us as a provincial government, this new center is both a reassurance and an opportunity. And why that is, I'll try and explain. In the early 90s, about 30 years ago, this whole region was dependent on two multinationals, both Dove and Philips. Then, in the course of, well, I believe it was just 1 week, one went bankrupt and the other went into restructuring, because at the time they employed about 30% of the population in this area, left us with approximately 15% of unemployment. As you can imagine, this was a big shock, and we had to struggle and find how could we overcome this. That took us a while, but as evidenced by the dynamism of the Brainport region today, we succeeded. And we did so through collaboration and the lesson that we should never become dependent on any one technology or one industry even anymore. Today the region is host to a multiple of industries and a lot of multinationals, all of which are regularly collaborating and influencing each other. Technologies developed in one industry are in the next month used by the other. Which brings me back to the Terahertz Center and why its founding is a reassurance for us. It is a reassurance because we know that with the inspired leadership you have, and with the multitude of talent collaborating within the center, and with the promise inherent in this technology, you will continue to diversify our industry. We know you will find those applications for terahertz radiation, and we know that some of you might even turn those applications into startups. And who knows, perhaps maybe you'll turn that technology and those applications into a new multinational. And that's why this is also an opportunity for us. The opportunity to support you in these endeavors by introducing your center to the wider industry inherent in the Brabant area. To support your startup ideas through initiatives like the GATE and Braventure, and in general help us build up that diversity of industry. So on behalf of the regional government, I would like to thank you for inviting us for this occasion, and I wish you the best of luck with your new center. Thank you.
Please, Robert Jan, an honor. So we now have the official opening of the new Center for Terahertz Science and Technology in Eindhoven.
Did you do the countdown?
I can do that. 5, 4, 3, 2, 1. We will now take some opportunities to take some photographs to mark the official opening of this exciting new center on Terahertz Science and Technology in Eindhoven. Do we have some photos? Yeah. Please. Okay. Thank you very much.
Thank you.
In the formation of the new center, we have diversity in the number of departments that are involved. We have diversity in the research groups that are involved. Academic professors with various backgrounds in applied physics, material science, electronics, and optics are involved. I would like to take this opportunity to welcome Professor Marian Mathers, Professor Jaime Gomez-Rivas, Dr. Doak Van Mechelen, and Professor Idelfonso Tafoy-Monroy to the stage. They will present the goals, the ambitions, the objectives of the Center for Terahertz Science and Technology in Eindhoven. Okay, so we're all complete. Okay, please, the stage is yours.
So also from our side, I would like to welcome everybody present here today in this room, but also the people online. Welcome to the launch of our new center on Terahertz Science and Technology, Eindhoven. So in the coming presentation, we will give a brief overview about our goals and ambitions. And above all, this presentation is also an invitation to collaborate, to join forces. Because as we have all experienced, this is a key thing to achieve in the current situation in the Netherlands, but also worldwide. We have to join forces and work together towards common goals. So also this presentation has certainly the ambition to invite people to collaborate with us in this new center and to join forces. Terahertz research and development is already a very strong area in the Netherlands. Here on this map, you see an overview of many groups that are involved in terahertz research and also industry related and interested in terahertz already. You see it is widespread over all areas in the Netherlands, from the north to the south, from the west to the east. And this gives the Netherlands, of course, a huge opportunity to excel in this upcoming technology. This is also recognized internationally. For example, the group in Delft is organizing now the IRMW Terahertz Conference, the Infrared Millimeter Wave Terahertz Conference, in collaboration also with principal investigators of our new center. So this is the biggest conference actually in the world in this area. And it will come to the Netherlands in the coming year. It will be hosted in Rotterdam. So it's organized by the group in Delft in collaboration with people from Eindhoven. So we're very happy and proud that this conference is coming now to the Netherlands. So overall, we see that terahertz is a growing area. We want to be part of this. And this is also one of the reasons why we have now created a dedicated center, the first center actually in the Netherlands dedicated to terahertz research. And with this center, we have a number of diverse goals. Of course, Terahertz Science and Technology is the key goal that we are following. And this is also one of the important roles of the university as a whole. So it's diverse. It has topics on material science, photonics, electronics, on devices, but also on signal processing. And we also thereby want to contribute to the entire development. And this is only possible when we also work on applications and on valorization. So, as you know, Eindhoven University of Technology is very strong in collaborating with industry. And we will also do this with this center. So the center is open to collaboration with industry. It's also open to explore new applications for people that are not yet involved in this new technology around terahertz. And we also will inviting partners to come to us, to join us in the lab, to join us in research projects, but also to valorize the new developments that we can foster from our center. And we want to do this also together with partners across the Netherlands, but also outside. And last but not least, one of the key objectives is also to educate a new generation of engineers and scientists in this area, in the terahertz field. And therefore, we extensively invest also time and effort into education. And this you will see, and you see it already in our bachelor education, in our master education, the PDN, but also in the PhD. In summer schools, in courses, in projects. And like this, we strongly want to create this new generation of engineers that need to know a lot, actually. They need to know from electronics to optics, from applications and from valorization. They need to know all of that and bring all of this to industry. They will specialize in some area, but the terahertz field is in between a lot of areas, and like that, they need to know also a lot of different topics. We are building a terahertz student lab. We have experience already from last academic year, and we will grow it even further. And we also aim to bring our students into the new terahertz lab that is also built up at the moment. So with this overview about the goals, I will give the word to my colleague, Jaime, who will talk you through the coming slides. Thank you very much.
Yes, thank you, Marion. So I want to motivate why Terahertz science is important, and the best way of doing that is by looking outside. So I took these images. This is M51 Galaxy, and these are images taken over a broad range of frequencies over the whole electromagnetic spectrum, from the X-rays up to radio waves. And astronomers know very well that in order to understand the universe, the only option is to look with multiple eyes, with super eyes, as Robert Jante Smith mentioned. So we need to look over the whole spectrum. So the same holds for matter, for fundamental research on materials. So if we want to understand matter, we need to probe this matter over the full spectrum. So we need to look also into infrared at terahertz frequencies. So I would like also to highlight that the visible spectrum, so the frequencies that we can see, is very narrow compared to the broad range of frequencies that cover the terahertz range and the infrared. So these are, again, the super eyes. There is a problem with terahertz, or there are challenges, of course, and this is the wavelengths. So these are long wavelengths. So we want to look also to nanomaterials, to nanostructure matter. So we need to concentrate, we need to focus, we need to also image terahertz radiation in small length scales, and we need to also to image this propagation of terahertz radiation. And this is something that we are working on in this Center for Terahertz Science and Technology, as illustrated in these 4 snapshots. So these represent a propagation of terahertz pulse over time, very short time scales, and over space. So these are techniques that we investigate, that we developed in the center in order to indeed investigate matter. And also something to mention is that we also pay attention, of course, into valorization. So we created recently a startup company, Terranova, which has as a mission to valorize this research that we do in the center, and also to indeed just make some valorization, concrete valorization of all this fundamental research. And with that, I would like to handle or to give the floor to Ildefonso, which who will also motivate the relevance of terahertz for technology.
So, welcome again, and thank you. I want to show you this picture, and this is how a mobile phone looked like 30 years ago. It took a lot of developments, a lot of breakthroughs in technologies, like having a lot of computational power on a chip, using new materials, and also integrating it in a system approach. And this is how modern devices look like this, and they're even becoming foldable. So it was breakthroughs in technology, breakthroughs in integration, but also, most importantly, looking at the whole system from the system engineering principle that brings things together, looking at the user needs. Another example, when you can visualize the importance and the impact of merging breakthroughs in science, biology, technology, with a system principle-based approach to the problem, most important in keeping the needs of the users in mind, is bionic limbs. So inspired by this, we would like to inspire ourselves and inspire you to work with us to boost strategic collaborations, to systematically accelerate developments in terahertz-based technologies, to create solutions with the user needs in mind. I chose to now share with you these pictures, and it's about a work going on in my team and also in the center, which is about creating structures that are able to focus and point the terahertz wave energy into a given space into a given point. This is going to be very important for wireless communications, but also very important for any type of application where we want to use and direct the terahertz wave into a certain point or sample. So it's going to be important for microscopy, for spectroscopy. And these are doing in integrating chips. So we have already done it for applications related to communications, but this is actually pictures of 3 generations of these beamformers. So some of them have been also done in cooperation with partners from industry, like Lionis here in the Netherlands. So this is to give you an example of how we are getting inspired to push these systems into a chip to make it more portable. So we're also working on trying to put generators and detectors and manipulators of terahertz waves in a single chip. It is our ambition and our power and passion to contribute to the development of full terahertz systems on chip. And this is an invitation for all of you to join us and collaborate as Marion started this speech. So we identified a few areas where we believe that terahertz has the potential and the prospect to make a big impact. Those areas are related to agri-food, to biomedical applications, to meteorology, energy, and systems. System ranging for how to guide a terahertz wave, for instance, via catheter to inspections of organs in the body, but also other areas that we don't know yet. Why? Because this is just an example of ideas that we believe are worth to put out here to trigger the discussions. So with this, I would like to invite all of you to join us, keep in contact with us, because our intention and our ambition is from now on, together with industry and academic students, stakeholders, to define more concretely the activities of the center. So with this, I would like to say just to you, please keep in contact with us. And here is an example of the email you can reach us. So with this, I hope that we have been able to present to you the ambitions, the motivations, and the goals of our center, but most of all, join us. Let's join forces.
Thank you very much, professors, for giving us that insight into the exciting program of the new center. Next on the agenda this morning, we have a range of presentations on the application of terahertz to various sectors, including astronomy, metrology, medical, and data communications. Therefore, we have a range of presentations and overview from academia and industry. Please note that we will not have so much time for questions. So for collaboration and any questions that you might have on the upcoming presentations, please send an email to us at ctste@tue.nl. So we have a range of speakers. I think a few of them are live and majority of them are online. So please allow us time to load the various presentations as the program proceeds. So our very first speaker will be online, Dr. Ulf Johansson. Ulf is an associate professor and photonics lead in Astron, associate professor in the electromagnetics group here in the electrical engineering department at TUE. He's working in integrated antenna systems, and he will be giving us a talk on towards terahertz frequencies in antenna systems.
I hope you can hear me. I'll just keep going. Yeah, thanks very much for the invitation to give a short pitch at the opening. I'm very excited about that. I'm very excited the center is finally there. And yeah, I was asked, and I will also give you an overview of the work that I have been doing in the past few years, and an outlook towards how what's needed then for terahertz. So my research is focused on active antenna research for millimeter waves and sub-millimeter waves. And what I have mainly been working on in the past years is on 5G related and antenna related topics. There's an overview here of all the different aspects that I've been working on, and I will go in more detail on the next slides. So it all starts with propagation research, because we channel, if we talk about communication, the channel is the only thing we cannot really change. The buildings are simply there, the earth is the way it actually is. So we need to understand how radio waves propagate through the environment, in order to know how to design our communication systems. And I just picked a nice picture here where we've looked into the reflection of buildings. So can you use buildings as reflectors at millimeter waves? So we have a transmitter in our flux building. So the people who know TU Eindhoven, they might recognize this building here. This is where the electrical engineering and applied physics faculties are located, with transmitter on one of the balconies. And then we used the mechanical engineering building as a nice reflector to measure the signal strength on the car park of this flux building. And as you can see, this fairly follows still what we know from lower frequencies, although the signal strength is much lower. But so this is something we focus on. We look into, okay, how does the channel behave at higher frequencies? Then knowing that, it's all about then designing the, so if you want to measure these kind of things, you need measurement equipment. That's also something that if you can't buy it, if it's not on the market, we develop these things in Eindhoven. So we've developed a channel sounder for millimeter waves for 28 gigahertz in this case, which is shown on this picture here. So typical performance parameters is that we have 3 transmit channels with about 49 dBm EIRP each. On the receive side, we have an omnidirectional receiver, and then we have an unambiguous range of 3 kilometers. We can measure up to speeds of 50 kilometers an hour, so we can also measure the dynamics of the channel. That was the idea in developing this kind of system. Now, if you know how a channel behaves, you can start to design a communication system. And the overall system, what we focus on is the antenna system part. So we've been looking into sorry for the background noise. We're looking into it's a classical phased arrays, which is something that people focus on mainly for 5G millimeter wave, are these kind of, we call them dense arrays. So that's one thing we look into, how do you integrate this together with the electronics. Now, one issue with millimeter waves is the efficiency of the electronics, and also the fact that the signal strength is attenuated much quicker than at lower frequencies. So in order to get a certain communication range, you need to either increase the power or you need to increase the antenna gain. Now, in view of the climate change and that we need to be energy efficient, we as antenna engineers, of course, vote for let's increase the antenna gain. How can you do that? Well, you can combine these type of phased arrays with a large reflector. So because your reflector is large, you have more antenna gain, you focus the energy really where it's needed, and in this way you can bridge larger communication distances. So that is something we have investigated. Or what you could also do, because this of course is fairly complex to develop, you've got lots of electronics in a dense space. One thing we also looked into, you use simply gain horns. They also have a lot of antenna gain, and now you could switch in between different gain horns and then focus the energy in different parts of your communication set. So these are ideas we've been working on in order to have a large communication range. Alternatively, what you can also do is you can have different type of antenna arrays with different distances between the elements. In this way, you can also create narrower beams and focus the energy a little bit better. In the Silica project, we've been working on a reconfigurable array. So this is kind of a test array where you can change the distance between different subarrays. You can use this as an analog phased array or a digital phased array. So this is a very versatile system. And talking about integration with the electronics, something we've been working on a lot also is the integration of the antenna with the electronics that is shown in this picture, where the antenna is integrated on the same chip with the amplifier. So that's things we've been doing. Of course, if you want to design these systems, you also have to measure them afterwards, and that is also one topic that we focus on a lot. That is, how do you measure at these very high frequencies? For example, if your antenna is connected directly connected to the amplifier on chip, there's no real terminal where you can connect your cable. And one example that is shown here in this picture, what we've worked on is that you can characterize the antenna without connecting it to a network, to network analyzer. So you don't directly measure it, but you measure it passively by radiating onto the antenna, measuring what comes back, and then what you need is 3 different loads, and then you can, without connecting to the actual antenna, you can characterize it. So these, I think, are the 3 different topics: so propagation, antenna design, and antenna measurements. Now, how does this link to terahertz? So 28 gigahertz is hardly terahertz. So I looked around a little bit for a nice picture I could show here, and I found one in my PhD thesis from a few years back, where my conclusion was, and I still believe that this is true, that if you look over frequency, then at lower frequencies, the antennas are probably integrated on a PCB or in the package of the IC. Now, frequency goes up, eventually we end up with the antenna being on chip. So, for about terahertz, we're certainly in this range. And now going back to the 3 different topics: propagation, antenna design, and measurements. Instead of a vision, what I did is I put down a few thoughts about these different topics and what's different now, what is something we have to look into. Propagation research, so we need channel sounders that don't readily exist at the moment. Things to look out for there is transmit power. The available transmit power goes down when frequency goes up. We have higher losses, so that's obviously something that needs to be taken care of. I think more importantly, we have the bandwidth. Why do you want to go to terahertz? Well, first of all, okay, there are more frequencies, so we can have new applications there, but also at higher frequencies, the instantaneous bandwidth is much higher. But if your bandwidth is higher, you also need baseband electronics that can handle this large bandwidth. And I think this is one of the big issues that we are facing to build a proper channel sounder. And measurement uncertainty. Again, the frequency goes up, everything, we measure in wavelengths, right? Everything is measured in wavelengths. So it doesn't matter whether it's meters or millimeters, it all depends on how large are the structures compared to your wavelengths. And as the wavelengths goes down, because the frequency goes up, then the uncertainty in our measurement systems also go up. So we measure something, but how accurate, how correct is it, that is changing. And that, I think, the uncertainty will be a big thing to measure properly. On the system design, I have a few more things, simply because it depends on your application. What is the wireless system used for? Is it a communication system? If so, is it a point-to-point system? Is it if you have moving users, so do you have to steer your beam? All that affects how you design your system. The efficiency must be high, which is the actual reason I would propose to put the antennas on the chip, because it should be as close to the electronics as possible. The efficiency of the electronics is also lower. So we really have to take care that the power we have available is really transmitted over the air and not lost somewhere between your electronics and your antenna. Again, frequency goes up, so the communication range goes down. So what we need to, what I put on here as well is if your wavelength goes down by a factor of 10, then your antenna gain needs to go up by a factor of 100. In order to maintain the same communication distance. So antenna gain is one of the big issues at terahertz. Beam steering, if we want to do that, how do we do that? Are we sticking with phased arrays, or are we doing beam switching? Are we using lenses? Are we using reflectors? So all these are questions that it depends on the application, but we might see a big difference here compared to the lower millimeter waves. Another big issue is that the amplifier, so antennas scale with frequency, amplifiers unfortunately do not. We already see now that at millimeter waves that instead of going from a small chip to a large antenna, the chip is fairly large as compared to the antenna. So instead of, we have basically a fan in. So we go from a chip and then we have to go to even smaller structures that then connect to the antenna. Packaging. Eventually, the antennas are on chip, beautiful, but you still need to package them. How do we do that? What kind of packaging technologies are we going to use? And after all, also, how much is it allowed to cost? So I think these are all the biggest topics I see for terahertz and the antenna system design part. And then finally, on system validation, dynamic range of your measurement equipment goes down as frequency goes up. Antenna efficiency is something we still struggle to measure properly. So what can we do there? We could use reverberation chambers. A colleague of mine is looking into this. Definitely a big topic. And system level performance is something, especially for antennas, we see becomes more and more normal. we don't only measure the antenna gain and the bandwidth and the input reflection coefficient. We have to measure what is the influence on the error vector magnitude and these kind of things. So I think we have to have more complex measurement systems to characterize the antennas. And having all this said, and I hope I stayed more or less within 7 minutes, I believe this is all teamwork, because it is things are getting more and more integrated, and I also noticed in the opening now that everybody emphasized this is a collaboration, and I fully agree with that. It is teamwork. We have to all work together, and I'm looking forward to working with all of you on that. And with this, I'd like to thank you all very much. And yeah, I suppose it's time for the next speaker.
Thank you very much, Ulf. Thank you, Ulf. So if you have any questions, please send an email directly to Ulf or to the center at CTSTe@TUE.nl. So next on our agenda is a live presentation by Professor Martin Polides. Martin is the director for the Center of Care and Cure here at TUE. He's also a professor within the electromagnetics group in electrical engineering. We will now hear about how to maximize the impact through collaborative research. The floor is yours.
Thank you very much. So it's very nice to be live here. So thank you for the invitation. Thank you for having all the people here, because I really believe in, let's say, personal contact. We were talking about it. For me, it really makes a difference. So I'm heading the Center for Care and Cure Technologies, and so maybe we didn't do as much research in that yet as the previous speaker. But I don't think that explains the potential there. The potential is major, and in this presentation I would like to enlighten you just a little bit. I won't go into the detail, but just some glimpses. But maybe first, centers. In electrical engineering we believe in the centers. And why do we do that? Because it's very difficult for researchers themselves, being sometimes a little bit on an island, to connect to all the world, let's say the players which are important in your research. Nowadays, all research is research for impact. And we need all the other stakeholders, but I also believe that they are very important. For example, if I look in the medical research, we try to connect the researchers from applied physics and electrical engineering towards the medical personnel, which speak a very different language. It's not always easy to connect. And then there's the industrial component. I think in electrical engineering and also applied physics, we are a bit more accustomed to that, but especially the medical part here is, I think, challenging. And that's why a center is important. And of course, we are very connected to the MTech program, the collaboration, the EASY Institute, and the health part at the other faculties. And of course, the new Materials Institute, which is being developed. So, just to give you one example here of where Terahertz can work. It's not research we did here, but this is by the Shanghai University in China. And they looked at, can we visualize brain cancer? And the nice thing of Terahertz is, regarding to optics, of course, they penetrate deeper, and you can also see different things. And I think in that sense, you can, let's say, look deeper, but also maybe improve the throughput, so go faster. So this is an example where there was a very effective discrimination between cancerous tissues and non-cancerous tissues. Of course, there is a lot of challenges there. Also, like in normal light, you have different colors, and you need to combine all that to make this image and to improve upon that. So that's where I think the center is one of the important things. And looking at, for example, how the Center of Care and Cure is organized, these are the roadmaps we made. So we have programs in perinatology, cardiology, oncology, and neurology, which are like the application domains. And we try to connect those to the what we call technology domains, which is MRI, ultrasound, monitoring. I think we should also say monitoring and sensing. And of course, AI and modeling is very important in this respect. Now, where do we see the Terahertz? Well, one obvious example is the one I just showed before, cancer detection. Cancer detection, I think, has been studied for quite some time in terahertz. It has promise, but bringing it to real-world applications still is a challenge. It's not a solved case. And I think we really need dedicated efforts to make this happen also in the clinic. So miniaturizing the devices, increasing the throughput, connecting to medical personnel to really what the specificity and sensitivity are. These kind of things we still need to, we need a lot of work in that. Well, the second example which we were thinking of is in the interventional room. So let's say the first pathology is really when tissue samples are sent to some pathology institute and they can be analyzed. Here we are really talking about in the OR. So during surgery or during a minimally invasive procedure, we really want to have the information from either the diagnosis, the detection, or maybe this catheter, which is the catheter location or the track. And these kind of reconstructions are very important and very difficult to do with current imaging modalities. But I also think that this explains why we really need the multimodality approach, because these ultrasound and MRI, they have a really important role already in the medical domain, and connecting that information to the surgery room is very important, and terahertz can have, let's say, a very big role there, to take all this information from these other modalities and to convert that into information which can be used during the procedure. And of course, I think, needless to say, in Eindhoven, we also look at artificial intelligence approaches to make that happen, to use this information and to exploit it really during therapy. So that's why I think that the center is really at the right time. That now is the time to really approach this, and I really look forward to let's say, join forces there. So here, if you look at this, this image, I think it's been shown a lot for collaboration purposes. But if you think a bit more clear about what is happening here, is they all have they have a common goal, which I think is very important. They also have a division of tasks, which I think is very important, and persistence, of course, to make this happen. And I think the centers are just that. Well, I think that the setting up the Terahertz Center shows the persistence of the researchers, and I hope we as a Care and Cure part, we can, let's say, help there. The common goal we have to define, and I think the road mapping can be a way to do that. And of course, the division of tasks, that's why I think different centers should work together to divide those tasks. And with that, I would like to thank you, and I look forward to a lot of collaboration.
Thank you very much, Martin. Very valuable insights. Next, I would like to, we also have a live presentation, and this is to be given by Dr. Shihab Al-Dafai, together with Dr. Simon Rommel, who's online. Dr. Shihab Al-Dafai is an expert on nanomaterials, nanophotonics, and together with Simon Rommel, working in the Terahertz photonic systems. Today, they're going to be giving us an insight into the integration route towards system on chip for Terahertz.
Thank you very much for this honored invitation here. So really, it's our honor to be me and my colleague Simon to present you how we see ourselves in this very exciting event, and especially in the center. So today I would like to share with you our roadmap to the Terahertz system on chip, and particularly with the Terahertz technology from devices on to system on chip enabled by photonics and nanotechnology. In the beginning, I would like to just reflect from myself how I came to this place. I mean, I'm originally from TU Darmstadt. I'm still in there as a group leader of NTT, Nanotechnology and Terahertz Systems. And then I joined the TUE in 2020 with the mobility grant. And then I already get a position in Skaltech. They will start soon in there. And then these two places also, they will a lot of collaboration in the future. So from that on, I would like to show you my research interest in current interest in the nanotechnology, or let's say in the nano devices, what we are already working on since a long time. So there is a lot of potential already mentioned before. I mean, it's very nice that I didn't want to explain you again the potential of the terahertz at all. So, but we need better, powerful devices, want to work on that. And this came from the powerful of the nanomaterials. And especially we use it deeply in devices. So this is why we're enhancing our devices using these nanomaterials. So another topic interest that after we enhance those core devices, we want to integrate them in the system. So we want to integrate the supported element in that to have these devices integrated. So this is the vision, how we would like to show you this potential. So here we integrate the lasers in the photomixers itself, and will make compact our devices, and we can provide this, and we go to our goal with the terahertz on chip. So with one of the topic that's interesting for us, make the big systems what we're just talking about, and especially big lasers, especially and also in the labs, and to have some of those parts for special application that we want to integrate those parts and make it really more efficient, and especially detecting in very small dimensions surfaces or biomedical or bio samples or fluids. So in this channel, this here, between the transmitter and the receiver, we can embed many, let's say, bio samples or microfluidic channels that we can use it for the terahertz detections. Other recent and very recent, few weeks ago, we get in touch with the very promising material, which is the carbon nanotubes networks, with very high quality of those material, and we can control them for both to be their conductive or dielectric, and use them also as sensors and enhancers for our devices. So this is a really very recent work in actions in our labs now. So after what we are already working on, always I have the experience to show that dreams, or let's say, I believe if Einstein living now, he will change his statement from imagination is more important than knowledge. I believe he will say experience is more important than knowledge and the imagination, both. So what I had my experience that whatever I believe in, let's say, 10 years ago or 5 years ago, it's happened currently now. So it's keep me thinking that, so whatever it's come to mind and really exciting, this will coming in true. This is why we keep going on in the future. So this is one of the future we are looking on, and we're working currently in that direction, really to integrate everything in the terahertz and terahertz on chip. So everything will be in that. But there is a lot of, let's say, complementary work should be happen. And this is why I'm talking about in this center, it will be a perfect platform for such a people coming from me and Simon to be involved and make this happen. Also, one of the very recent research, and never happened till now, that the programmable terahertz devices appear till now. And there is very specific application for that. You have to believe we're talking a lot about photonic integrated circuit, and after we're done with those, what happened if we want in next year to upgrade them? If they are in the space, you have to think about it, what we have to do. To launch another shuttle to send the new chips over there. But if we have those devices, we can program them remotely, and then they can update themselves in the new operation. Or if they get damaged, So we will believe in one day we will have some system to correct themselves, and they can generate a new connection to another devices to make them operation again. So they can help themselves by themselves in the future. This is what we are looking in the future, and I believe we are coming to the right platform to do that. Another topic which is really very recent, also a lot of people thinking about it. So we are believing on one day we will have terahertz processor, that all things is happen in the terahertz domain inside the chip itself, after we having the connection to the outside world. So this is one of the, let's say, not the dream now, because we as a scientist, we don't believe on dreams, we believe on facts. And this is why we really wish that, and we're working to make that happen. So, and the recent, after that, what is really in our part is in here, especially in TUE, we're talking about many founders and fab, they do their own process design kits for their photonic integrated circuit. But anybody heard about terahertz PDKs in the world? Not. And this is why we really want to insist to establish this, let's say, research and activity to make it happen in this center. This is one of our goals, and I believe we all will sit here and will celebrate again to release the first PDK from terahertz from here, from Eindhoven, and from this center. So by this, I would like to also be fair and give some few minutes to my colleague, Simon, to say some word about his activity. Thank you very much.
Yeah, okay, thank you very much, Shihab. I'm not sure if you can see my slides as of now. I think it is very interesting, the things that you mentioned, and everything that you have shown on the integration side. I think if we really want to maximize the value that we can get out of the things that we actually do in terahertz, and if we want to make sure that we can bring this towards the applications, then I think we need to take very much a systems level perspective on these things. And I've listed here some of the applications, but they were already mentioned earlier on, so there's probably no point in reiterating them. What I think is very important to point out or to mention is that many of the challenges that we see across these applications will come from the same directions. And we want to see if there is similar strategies that we can find in order to address those. So of course, we have the generation and the manipulation of the terahertz signals, and we here in Eindhoven, and personally myself, I believe that photonics is ideally placed to actually help us in the generation of terahertz signals and the manipulation, the actually conditioning of our signals to the point that we need them. And of course, this then goes very much into the direction of what is the signal qualities that we're actually looking for. And here, then, of course, the different applications will have different needs, different focus. And I guess the purity of the signal is very key for some of the applications. Many applications will be looking at tunable signals, at reconfigurable signals. Of course, then that also gives us the versatility of the entire system, and of course, getting sufficient power out of the terahertz signal generation is very key. So I think these 2 points are very much where we can already take technology that we know today and that we have seen just now presented from Shihab, and then we want to extrapolate from those, and we have to see how can we get to the point where we not only have a terahertz PDK, but where we can make sure that we can actually integrate the entire thing also with the radio frequency parts that have to be before or after, as well as the photonics and of course the terahertz itself. And we want to really look at design, packaging, and the integration of those. Finally, I think it is very key that we see also that the control signal and the signal processing actually is something very important and something that really determines the value of what our system can do. And here, of course, then we have the entire surroundings of these chips that we always show and that we're very proud of designing and working with. But I think looking at how does this fit an overall system and making sure that the system is actually tailored to the application is very key. And then, of course, as the people in the middle that look at the systems level, we really have to make sure we get good feedback from the applications, we collect the requirements, and we keep the interaction alive. We have to be the linking pin between the applications and the devices and the components to make sure that on the systems level we're actually able to operate. And then on one application that I've been working on quite heavily before, and I think that is definitely very key, is the communication side. And I think here we have a very strong background in TU Eindhoven, both on radio communications as well as on the optical side. Myself, I come from the optical side, and I have though been working really on the sub-terahertz, maybe on the millimeter wave side, to try and bring the things that we can do in optical communications towards that side, pushing, of course, capacity. And I think terahertz here is offering even more capacity as we have more spectrum. So I think that's one key point of why do we want to do communications at terahertz. But then also to see that the need for spatial control, of course, has been something that we've observed in radio networks for a long time. And I think when we go to ever higher frequencies, it becomes more and more key. Since we have less energy available, we have to focus it more, as I think was already mentioned before. And of course, then here optical beamforming, still MIMO technologies or reflective surfaces are quite key things that we're investigating, and we of course plan to investigate further. And then we also want to see that terahertz is not only an extrapolation of what is currently done in radio systems, but I think we should take terahertz as an opportunity, as a new frontier, to see what can we actually do beyond what is currently done in radio systems. And I think here physical layer security is something that we as a group have touched upon, looking at noise buried signals, looking at chaotic oscillators, etc. I think terahertz is a prime candidate to see if we can do things similar to what is done in quantum key distribution in optical fibers, to see if we can establish something like this also wirelessly. Of course, that would allow us to establish a quantum secure communication domain from the optical networking and the entire infrastructure towards a wireless end device. So I think that's a very key point that we're really starting now to look at with quite a lot of focus. And then, of course, we have to see how does this behave in a very much shared channel, since we want to transmit wirelessly. How does this impact the security side of things? And of course, how can we really have both a secure channel and a data channel on the same terahertz wireless link? And with that, I think both my time is over, and I would want to say thank you to all of you, also again to Shihab. And maybe I want to apologize for not being with you in person. That was not planned, but due to the current situation, I have to isolate myself at least for today. So thank you for giving us the opportunity here. We're very keen on collaborating within the center, and of course with all the partners around the center in Eindhoven, in the Netherlands, in Europe, and worldwide. Of course, I think it's very key that we try to collaborate and work together and make as much as we can out of terahertz.
Thank you very much, Simon. Thank you, Shihab. So for collaboration, please send your emails to ctst@tue.nl. So our next speakers are online, so we're switching location to TU Delft. So online I have Professor Nuria Lombard-Juan and Professor Andrea Neto. Both are from the Terahertz Sensing Group at Technical University of Delft here in the Netherlands. So we will be getting an insight into the terahertz activities there in TU Delft. So I think the slides are on. The floor is yours. I think just a few minutes until we load the material. Great. Our speakers are joining us very shortly.
I hope you can hear me now.
Perfectly clear. The floor is yours.
Okay, thanks a lot. So good morning. My name is Andrea Neto. I am the chair of the Terahertz Sensing Group in TU Delft. And first of all, I would like to thank you a lot for the invitation to this event. I'm extremely happy that there is this new center in Eindhoven about Terahertz technology. And I have to say that even if it's in Eindhoven, I'm still happy because after all, Eindhoven is where all the industries are and where things will eventually happen in this field in the Netherlands. We present our group. We have been founded about 10 years ago, where I joined university. Before I was at TNO for another 10 years. And our group is composed of about maybe 25 people that work every day, plus a number of master students. About 1/3 of us are physicists, and the other 2/3 are electrical engineers. I am an electrical engineer originally, but because, as it was mentioned, Terahertz is a very multidisciplinary field, we need continuous contaminations from physics as well. And let's say what you see here is that, there is a number of students from all over the world, and they all look happy at this moment. Let's say our background essentially is in 3 fields, which are distinct but very tightly connected. I myself, I try to cover advanced antenna architectures and more on the electromagnetic side. Then there is Dr. Jochen Baselman, which is both with us and with Esron, half and half. And he's covering mostly astronomical instrumentation. And then we have Nuria Lombard, which is essentially covering quasi-optical systems. The 3 of us are full professors, and each one of us won a different ERC grant on advanced antenna architecture, instrumentation, astronomical instrumentation, and quasi-optical systems. So we are very complementary, and we work together on virtually almost every topic, I would say. And complementary and very good as well. And let's say our biggest collaboration, and that's historically the reason why this group exists. Before there was the only real interest for Terahertz was in the space investigation. So we have had a very long, I personally, 25 years of collaboration with Esron. They even paid my PhD a long time ago. But now they are the Terahertz component, Terahertz part of Esron that does research is embedded in our group. So they have a laboratory, a cryogenic laboratory where all their superconducting, supersensitive devices are being measured and characterized before being brought actually to telescopes. They go regularly, once every 2 years, they go to the Atacama Desert in Chile, where they have access to a big telescope via the Japanese science delegation. I don't know how it really works, but every 2 years they go there and they test receivers, which are being designed in our group. And this is our hat in the Atacama Desert a couple of years ago. This is the strongest and more lengthy collaboration we have had. The reason for existence of this group and why we had to start working for Esron was that as the frequency increases, as it is already been mentioned before by Wolf, things become more difficult for antennas. So essentially, low frequency, you have big antennas, they are much bigger than the electronics. 10 gigahertz, they began to be comparable, the chips with antennas. And this is a design which was working at 1 terahertz in CMOS, and you see that the electronics to feed this array of 8 elements is much larger than the antenna itself. So actually, as it was anticipated by Wolf, it really makes no sense to have separate antenna and chip when you go above a certain frequency. Now, this frequency is very high. It was for 1 terahertz. But I would say already when you are in around 100 gigahertz, you should start to think about where you want your antenna to be, because it depends on the actual compromises that you're going to do in your system. If you want it integrated or in package, most likely it's not going to be on PCB anymore. This is, for us in this moment, we have always been in science and sensing for about, let's say, 7 years, and before that, much longer, more like 20 years. But since about 4 to 5 years, we feel like we're in a gold mine. We're receiving an immense amount of requests for help in developing our frequency systems, because the entire architectures which can work are completely different from the ones that can actually work at much lower frequencies. We come from the low frequency of the spectrum. Because of the fact that the antenna is so important. Very often we have to deal with chip designers, which historically were less prepared on electromagnetics and waves floating around the circuits. And when you have the antennas which are integrated in the chips, then you have a new field where essentially things are very complex. So what is our strength? What do we bring to this field? Essentially, we work always, since 10 years, all of our work rotates about around 4 concepts. One of them is the artificial dielectric layers that we use to enhance the properties of antenna radiated when they are embedded in chips. So these antennas essentially were embedded in chips like in CMOS, for instance. They typically very inefficient, so it's only by accurate co-design of the antennas and the surroundings that you're able to actually have the power and emerge from the chips without surface waves. And we have prototypes to demonstrate the efficacy of these at 10, 70, and 300 gigahertz, where we hold the records for these kind of structures. Then we work on connected arrays that are a new type of wideband arrays that are able also to achieve wide scanning angles. And here again, we do prototypes. So actually, we have done these also at 1 terahertz. This must have been also 1 terahertz, but mostly the know-how comes at low frequencies because we have lots of requests for communications in 5G. And now we are proposing it also for 6G in the hundreds of gigahertz ranges. We also have prototypes there. We work on dielectric lenses. This mostly was born with Ezron. And here the problem, the electric lenses in terahertz have a bit the role that reflectors have, because essentially they guarantee the capacity to focus a signal and having a good front-to-back ratio. And so we have developed prototypes over the years from 3 gigahertz to 3 terahertz. The reason why I show these numbers going from low frequency to high frequency is that typically, because there are costs and difficulties associated to developing a new antenna concept at high frequencies, we always first make prototypes at low frequencies, make sure that we understand how the thing works at low frequencies, and then we go on to the full integration and the characterization, because the manufacturing it at high frequency and characterizing is much more difficult. So you want to do it once you already know that you have and more expensive. Once you have a concept that already know it works. And then, of course, we're also very, very good at quasi-optical systems, where essentially we define arrays that are typically, instead of using phased arrays at very high frequencies, one tends to use staring arrays. So arrays of elements, each one of them look in a different direction. And for those, you have to dive deep into the design of quasi-optical systems, where as I mentioned, Luria Lombard is one of the main players. So these are our strengths. I'm going to make you just a couple of examples about systems which are innovative. One is a flagship for our department on terahertz communication. Because at terahertz there is a very large spectrum available, what we plan to do was we imagined as a scenario where we would have the biggest benefit is stadium-like scenarios, where we imagine that in order to cover all the people that want to connect wirelessly, instead of having a number of low-frequency antennas, we're going to only have one base station in here. It's going to host about 1,500 smaller antennas. And these 1,500 beams are going to be oriented to the various portions of the stadiums. And this can be done also for smaller venues, of course, but the stadiums are really the structure that we're thinking about. And these arrays are going to be integrated on a printed circuit board, but they're going to have a number of lenses, thousands of them essentially. And underneath each one of these lenses, there's going to be a number of feeds so that we have a number of beams coming out with each one of these lenses. And we call these the fly's eye system because overall these lenses will look like a fly's eye. We are working actively on this since many, many years now, maybe 5 or 6 years we're working on this. And the prototypes we're developing on are around 130, 180 gigahertz. Our system design involves having an overall capacity of 10 terabytes per second with more than 1,000 beams. So I think we're going to get some demonstrations in the next couple of years of this concept. And the other topic I'd like to touch upon that in this presentation is the hot conductive antenna radars. And the 30-second story is that to generate power in the terahertz field, it's very convenient to start from optical power, pulsed laser systems, which are commercially available. This one is a system from Menlo that we have acquired a couple of years ago. Typically here you have antennas that are called photoconductive receivers and photoconductive transmitter. The power is generated when the optical signal impinges in the semiconductors and generates as a response a Terahertz signal. Well, normally the samples are located here in the middle between the transmitter and the receiver, and that's because there is not so much power available. If you had enough power available in this conversion, then you would be able to locate, to point the transmitter and the receiver toward a target which is located far away, and then you would realize what effectively is a radar. Well, the third and second story that I'm telling you now is that now we have about 1 millibit of power measured, which we think corresponds to about, on simulations, about 4 milliwatts of power generated. So I think essentially we have enough power to actually develop a radar in this domain. It would be essentially something like a LiDAR, but operating in the terahertz range. And we have record power in here. I'm going to show you just the numbers. This is the measured power, 712 microwatts. That was measured at Leeds, and not even in our institution in England. And well, the power that we measured is about 50 times higher than commercial available sources like the Menlo system alone with its owned antennas. And not only it is very high power, also the spectrum is actually designed to requirement. We have designed this system to operate until 600 gigahertz. And you see that we have very nice, almost flat top until 600 gigahertz, and then it goes down. And we see that the spectrum is also repeatable for very many different combinations of biasing and powers. So essentially, there are lots of advantages in working in the terahertz. For a scientist working in a university is that when you do something new and it works, you don't get like 1 dB of improvement. You improve it by a lot because there is really a lot of space in the terahertz field, lots of margin of improvements on what is the state of the art because, yeah, many people stay away from terahertz. At the department level, we need to collaborate with everyone. So we collaborate very strongly with the microfabrications facility. So we have a clean room, EKL, and ECTM is the group that runs it. And we have the ELCA, the Electronic Research Laboratory, the electronics group. We collaborate very well with them. They're very good at measurements. Actually, we buy all the equipment together. And we do mostly the conception, the design, and the characterization very often is done at ELCA. Okay, so we cover the entire band in here. A final thing, how we work, we typically work very much at low TRL level and let's say 1 and 2, and most of the other work in which we arrive to demonstrating capabilities goes with partners, and historical partners are ESRON and NASA, with the European Space Agency, TNO, where we always worked in the past. With NXP, we are collaborating on radar technology. It's not terahertz, it's 100 gigahertz, but okay. We call that terahertz as well, and IMST for communications. And I thought this was more or less what I could have told you because, as I said, we exist since 11 years. We have done so many prototypes, and we touch upon most of the applications which were mentioned, even though, as I said, no, we don't have a center as organized as Eindhoven. So very much we have to resort to coupling with the industries directly. Now we look forward to collaborate with Eindhoven. We're already doing it in the organization of the conference of 2022 in Rotterdam. And yeah, very thankful for the help of Jaime and Duco in organizing this conference. And I think it's going to be an event that's going to unite our Dutch community. And I think this was what I wanted to share. So thanks a lot for your attention. And I'm gonna...
Thank you very much, Professor Neto, for providing a very extensive insight into the activities of your group in Technical University of Delft.
Yes.
So as we load the next online speaker, I would like to briefly introduce her. So we have Professor Britta Redlich. So Professor Redlich is Director of the Free Electron Laser Facility, abbreviated as FELIX. And she is also the group leader of the FELIX Infrared and Terahertz Spectroscopy. She's also professor at Radboud University, and she's going to be giving us an insight into the activities both in the FELIX facility and also at the Radboud University. please allow us some time while she connects while we add her to the Zoom channel and also load her material. In the meantime, of course, if you have any questions for any of the speakers, please send them an email individually, or you can contact us on ctst@tue.nl. Floor is yours, Professor Redlich.
Thank you very much for this invitation. I hope you can all hear me. Thank you very much for this invitation. I hope you can hear me and see my slides. Because in the YouTube channel, I don't see that yet. Okay, I'll get started, I guess. Thank you very much for the invitation to join you, unfortunately, virtually on this exciting day of the launch of your new center. It is a great pleasure for me to give you on this occasion a flavor of the science that we do at Radboud University. I still see the slides flipping on the YouTube, so I hope you can see what I'm talking about in a minute. To get you started, okay, there the slides come as well. To get you started, I would like to introduce our HFML Felix research facility. As you may know, it is a large-scale research facility where we are building magnets and free electron lasers in the terahertz range. We built this instrumentation in order to run our own scientific program on discovery, but moreover, we are also operating an international user facility where we serve users from all over the world that come to us from academia and more importantly, also from industry and private partners. We built this instrumentation, as I said, and in the next picture, you will see that we have all kinds of terahertz sources that we all together develop. Our infrared and terahertz free electron laser are a different kind of source, not miniaturized at all. What you see here is an overview of the accelerator vault where the suite of 4 free electron lasers is placed. You have to imagine this is a vault of 20 meters long, 10 meters wide, and actually in my background, you see me standing in this accelerator vault, and I'm a little bit taller than the free electron laser's height, but this is a guess of how it would be if you could visit our facility. So these free electron lasers cover the entire terahertz range, as you can see indicated in this slide. Moreover, they provide very high intensities, high peak brightness, and a very high time resolution that we can use for the different research that we want to pursue. And users usually combine some of these capacities in order to answer their research questions. We've already been talking about super eyes, and from a fundamental aspect, I would like to show you one aspect of terahertz radiation that is very important to make this super eyes work. And this is the molecule that I show you here. The molecule on the left-hand side vibrates very locally. So you can see there's only small movements in the molecule, whereas on the right-hand side, what you can see is that the molecules start to vibrate very much to perform collective motions. And this is a very important aspect. In the left-hand side, we have shorter frequencies. If we tune to longer frequencies into the terahertz, you see this motion start. And if we can combine all this information, what we will do is to record a molecular fingerprint or a fingerprint of matter in general. And this fingerprint relates to structure and functionality. And this is what we use in our experiments. And well, when I talk about a fingerprint of all the matter around us, you can also imagine that applications of this terahertz free electron lasers range very broadly all the way across physics, chemistry, biology, material sciences, also astronomy is involved. Well, from our research questions, very often they are fundamental, though we try to connect to societal challenges and applications. And the applications at HFMR Felix that we see are in areas of impact, most predominantly in health, energy, and smart materials. These are exciting areas, and I will, in the remaining few minutes, take a moment to elucidate on each of these topics one key example. It's fundamentally motivated, but you will see how that connects to applications and problems. The first example I want to show you here in this presentation concerns health and the search for novel biomarkers that we are interested in. This research is done in strong collaboration with the hospitals, with the colleagues at the hospital, and it concerns biomarkers that we look for identifying metabolic diseases that are very important in young children. There are many of those diseases, and they can have very severe impact on the health and even cause death in young children. Well, if you diagnose them early, though, they can be cured easily, or many of them can be cured and prevented easily. So we really want to find biomarkers for as many of these diseases as we can. Of course, the hospital has own apparatuses to do that. They know many biomarkers, but quite often they come to a point where the pinpoint towards one specific biomarker is not so easy. And in those occasions, what we will do is we identify with the terahertz spectrum, as you see it here in the picture, we identify uniquely this biomarker, and hopefully from this part, it will then join into the newborn screening, as you see on the right side, what we call heel prick, and help to early diagnose a disease that can cause severe health issues for a child and help to prevent it. The next example I would like to show you very briefly is related to energy. This is where we look for materials that could help to find energy efficient data storage means. As we all know, our need for data centers and the growing capacity that we need is growing very rapidly and probably soon coming to a level that's unsustainable. And so this research, as it is depicted on the right-hand side, is motivated by the search for materials, magnetic materials that can facilitate switching at a much lower energy level as we currently do. And here we use terahertz pulses in order to do that, and that we can have demonstrated already in a time-resolved fashion, as you see in my next slide, where we show the magnetic switching of domains induced by a very strong terahertz pulse. And the idea would be that we could encode energy much more at a very much reduced energy level, information into these magnetic materials. The last example that I would like to show you in my presentation concerns smart materials. A type of material that we want to investigate is shown here. It's called single fission materials. These are organic materials that have the capacity, if they're irradiated, for example, with the blue photon, as shown in this slide over here, to split this photon into 2 photons, so actually doubling the number of photons that we can receive from the solar system, and thereby doubling the capacity. And the interesting thing about that is we do that in the terahertz range, because also there the terahertz range is the interesting range for studying these materials in detail. However, in this particular case, we also add one additional, and now I come back to my introduction slide, axis of exploration, because for these research lines, we can couple the free electron laser, the terahertz radiation, to high magnetic fields. So we have another extreme condition which we can impose on the material we want to study, and thereby have an additional magnifying glass that we can look at more details in these type of materials. A unique combination that we can offer and that we use in very different directions, also in superconducting materials, quantum technology, and so on. Well, in view of time, these were the examples I wanted to show you today. I want to go back to what was said in the beginning. Also, we like strong connections and networks, so we operate worldwide. You see the users of the facility indicated on this slide, and also the Dutch user community is, of course, very important to us. So we would really cherish joining forces, and we hope that we can make a very strong connection to the Center for Terahertz Science and Technology in Eindhoven. And with that, I would like to congratulate you on the launch of your new center, and we wish you a Terra bright future. Thank you very much.
Thank you very much, Professor Redlich, for the fantastic insights into the activities of your group and the activities at Felix. To continue with our exciting program for today and to give our colleagues time to load the next presentation, I urge you that if any of the presentations have triggered any urges to collaborate, please contact us on CTSTe at TUE.nl for information on any of the material that you've seen today and also on collaborating for the future. Our next speaker is Professor Andrei Barishev. He's a professor at the Captain Astronomical Institute at the University of Groningen. So we are switching our location online to Groningen. His research is in the area of astronomical instrumentation for infrared and sub-millimeter waves. He's also a co-founder, a co-owner of the startup company Dutch Terahertz Inspection Services. I think we have our speaker online. Professor Barishev, the floor and the screen is yours. Thank you.
Good afternoon. My name is Andrei Barishev, and I'm working at Captain Astronomical Institute in Groningen. So I represent here NOVA, Dutch School for Astronomy, and University of Groningen. For already more than 30 years, our group, which consists of approximately 11 staff members, PhD students, and postdocs, are busy with development and using sub-millimeter wave instrumentation for astronomy. I specifically don't use the terahertz as a word. It's of course very fancy word, but historically it started as a sub-millimeter, and historically we are developing coherent detection technologies. That means we detect not only amplitude and phase. And astronomy is a frontier also for technology, because it is very important to have an instrumentation which expands your view on the universe. And the terahertz, the sub-millimeter wave band, was and still is a little bit of a dark spot of our knowledge of the universe. That's why there is a lot of focus in development of astronomical instrumentation in the sub-millimeter wave regime, and we are actively participating in that. As you see here in the background, here is the ALMA telescope, and we are the main developer for the instrumentation for the ALMA telescope. But now let's focus, what is it we can actually see in the sky? And this is the collage of the pictures which represents the major advances only for the last 10 years or even less. Some images are only 3 months old. So as you see this on the left, this is the image of the debris disk done by ALMA telescope, which is measured at 230 gigahertz. And this image has 10 times better resolution than Hubble telescope. As you see the rings, you just don't see the planet between the rings. And this is the next goal for ALMA telescope, to achieve it in the next generation receiver systems, which we are also participating to develop. And here you see the zoom in the 1AU system, where the Earth is supposed to be, well, relative to that system. Here you see the zoom out, the Milky Way in sub-millimeter wave. This is the large survey using, which is done by 12-meter dish Apex telescope, which is in Atacama Desert. Here you see the major results from Herschel, which can probe where the water on Earth comes from by measuring the deuterium to the normal hydrogen ratio in the water around the comets, which can be compared readily with the same value on Earth. And here to the right, you see a very nice picture of the protoplanetary disks. Before this picture was done by Alma a few years ago, it has been believed that the protoplanetary disks do not have such a diversity in the structure. Now it has been discovered that there are many ways the planets can be formed, which would be a breakthrough in the theory how, in the modeling on how the planets are formed. And of course, the latest and the greatest, the image of the black hole, which was also done in sub-millimeter in 230 gigahertz range by the global set of the telescope, Event Horizon Telescope, where the data has been recorded and combined. So the terahertz astronomy, sub-millimeter astronomy, is a very important field, and there are many breakthroughs because we are coming by our technology. So what actually do we do? So the typical system, telescope system is constructed as on this slide. So we have a radiation from the sky object which comes to an antenna, a terahertz antenna, to be as large as possible. For instance, ALMA is 12-meter dish with roughly approximately 16 micron RMS surface accuracy, and then all the energy is then concentrated on the front end, which is in our case a cryogenic front end. So we operate at 4 Kelvin. We use this. We design the insert for the front end, which contains the quasi-optics, and then further all the radiation comes to the core of these optics, superconductor isolator, superconductor mixer, and this is what we are developing. So we have developed the mixers for 650 gigahertz, and inside the mixer we have the very tiny waveguide structure, thinner than the human hair, which we machine, and on the detector chip we have a very thin layers of superconductors and dielectrics, and finally one square micron device. So we basically get all the signal from this rather large antenna and concentrate it efficiently on 1 square micron device, which is at a cryogenic temperature. Why cryogenic? Of course, we want to get every sensitivity we've got here, because we don't want to lose any photon from the source, because they are very weak, and the more sensitive we are, the farther we look into the atmosphere. So this is our research. We do this research, of course, in the collaboration with all the parties, with the TU Delft, who was providing the superconducting technology and also some antenna designs. We also do the characterization of quasi-optical systems, but we are very much oriented by application of these quasi-optical systems to the radio astronomy. So here is a snapshot of our recent receiver development. So we pioneered the sideband separating receiver, which allows us to reduce the atmospheric noise twice at 650 gigahertz. This is the first ever receiver built for such a high frequency, and recently we demonstrated such a receiver at 950 gigahertz, and that basically means almost a terahertz officially. We have the best sideband ratio, that means atmospheric noise rejection above 15 dB, and rather competitive noise temperatures. And very recently, for Event Horizon Telescope, we have developed the quantum limit to 130 gigahertz mixer, where we have a physical problem that we know that our system is limited by the quantum noise, but no one has come actually very close to the quantum noise itself. It's a separate physical problem. And here we see that we are actually touching the one quantum noise curve by our actual measurements. This is really a basic physics ongoing in a terahertz as well. So I just gave, in a view of time, I gave you just a little snapshot. So we are developing the terahertz systems for astronomy. So, and for that, we need a lot of technology developments and collaborations, because we cannot develop it all ourselves. So we first developed superconducting quantum limited mixers and receiver. And for that, we need a technology of the micromachining, technology of the characterization. We, of course, need a local oscillator sources. And here our collaboration with TU Eindhoven comes to play because many of the terahertz oscillator sources are harmonically generated. And that here comes the effort of Marion Matter's group in this. So we are also very interested in high-speed digitization. which may be not a part of the Terahertz Center, but it comes very close to it, and I know there is a very good group in TU Eindhoven doing that. We are interested in theoretical and practical systems in the terahertz which have extreme wide bandwidth coupling, both on chip and quasi-optics, and we are interested in collaborating with TU Eindhoven with that, but not only with TU Eindhoven, with all people who are presented today. And the next step in astronomy, so we are in actually a groundbreaking transition. The terahertz technology, as you have seen many very nice talks here, is advancing very rapidly. And so it comes very, very much closer to realization of the systems of many components. Because until now, astronomy dealt with unique single pixel receivers. The array receivers in heterodyne was scarce, maximum maybe 32 pixels, and with not a great performance. Now everything comes together with the effort of this community that we can talk about 1 kilopixel focal plane arrays for doing radio astronomy with a very high frequency resolution. We, of course, are also specializing in receiver system characterization. For instance, the latest effort, we, together with European Space Agency, participated in characterization of the JUICE satellite antenna. This is only 30 centimeter antenna, but it is actually the terahertz antenna not so big, especially if they are going to fly to Jupiter. So we analyze in the data which we obtained with the cryogenic system of characterization of terahertz antenna. This is another aspect which is very important. And very important in all of this is miniaturization. As much as possible should be integrated on the chip to achieve the large format focal plane arrays. And there, this is a direct link for the Terahertz Center development. There are many links in what we are doing in, with the Terahertz Center in TU Eindhoven. So in a view of time, this is the collaboration directions which I want to outline, and we want to work together. And it is especially nice that we have also a symposium to discuss all of that in phase. Unfortunately, I couldn't make it to Eindhoven. In our future, just to outline that we still have a lot of interesting projects ongoing. Some of them we need to finish, like 24 kilopixel camera in IMKit. This is a collaboration with ESRON, Max Planck Institute, and TU Delft. Millimetron, this is the new Russian space mission, which needs a lot of the technology what we are developing. Next generation of Event Horizon Telescope, a community of all the telescopes, they all need a quantum limited receivers and receiver systems characterized. And of course, our main experimental working horse, Apex telescope, as you see me cycling in front of this telescope several years ago. We are still collaborating and delivering the terahertz system. Hopefully, we can then extend what we can achieve in astronomy through the collaboration with Eindhoven Center for Terahertz Technology. Thank you very much.
Thank you very much for your interested insights. Much appreciated. So in view of time, we continue with our program. So we have the next speaker is Dr. Anselm Denninger. He's a product manager at Toptica. So Toptica Group specializes on diode lasers, terahertz systems, and frequency combs for terahertz applications and biophotonics. So he's a product manager, and he's going to be giving us an insight into the terahertz from an industrial perspective. Please, I urge you to stick to 5 minutes because we are running out of time. Thank you very much. The floor is yours.
So hello, welcome everybody. Thank you for giving me the opportunity to participate in this inaugural event. Since we are a bit late, I will give you a truly ultra-fast presentation of Toptica's terahertz activities. An industrial perspective. 2 years ago, I found myself contributing to a review paper on industrial terahertz applications, and I summarized the perspectives given in 5 different market reports. As you see, the 5 forecasts from companies in China, Ireland, so that still presents a bit of a chicken and egg problem. It is widely agreed that prices will drop once the volume grows, and the volume will grow once prices drop. So allow me to share with you how we at Toptica began our terahertz activities. So indeed this year, we are looking back at 14 years of terahertz system design. Initially working with the universities of Frankfurt and Darmstadt, we built our first continuous wave system for the Laser Munich trade show in 2007. Today, we are looking at more than 200 complete systems and over 700 lasers for terahertz generation in the field. We have 3 main product families, the TeraScan, the TeraFlash Pro, and the TeraFlash Smart, designed for different applications each. So let us quickly look at the first system, the TeraScan. It is a continuous wave platform which translates the difference frequency of 2 lasers into terahertz radiation. Since we can control the laser frequencies very precisely, we can also adjust the terahertz frequency in very fine steps. So in the language of our marketing division, this is the record resolution system. One application that benefits from the high frequency resolution is trace gas sensing. At low pressures, absorption lines narrow to megahertz widths. Here you see a close-up of an SO2 absorption line, absorbance versus frequency. The line shape with its half width of 7 megahertz is clearly resolved. The TeraFlash Pro enables broadband time domain spectroscopy and imaging. Our marketing friends call it the record specs system. Indeed, we routinely achieve bandwidths beyond 6 terahertz and a peak dynamic range of more than 100 dB. The high bandwidth is an advantage for terahertz imaging. Here you see a reflection image of a resolution pattern. It does not seem too spectacular at first. However, we can use spectral filtering in image post-processing and use only frequencies above 3 terahertz. Then, all of a sudden, we resolve very fine structures down to 250 microns. Not long ago, commercial systems would not even reach 3 terahertz, and now we have so much signal that we can afford throwing all of the lower frequencies away. Finally, the TeraFlash Smart is also a pulsed system, but it uses 2 synchronized femtosecond lasers rather than just 1. This enables terahertz measurements at record speed. The system acquires up to 1600 pulse traces per second. One promising application is the measurement of the layer thickness of paint. In the example, you see a reflected pulse of a 13 micron epoxy layer on metal. The layer boundary is not really visible with the eye, but can be determined with mathematical modeling techniques. So we are confident that various industrial applications will benefit from the high measurement speed. First examples include a robot-assisted system for measuring car paint layers, or a setup that measures the thickness of plastic pipes in extrusion lines. To conclude, terahertz technologies have come a long way from the initial clumsy lab setups and have found their way into real-world applications. Thanks to advances in system size, robustness, and performance, Terahertz screening can measure thickness and detect faults, well, mostly. So this guy says, what a strange signal. I wonder what's wrong with this batch. And here, hidden from view, you have some vicious mice who sabotage your production line. So let's be fair and say Terahertz screening can detect almost anything. Thank you for your attention.
Thank you very much for that fascinating insight. Thank you very much. Really appreciate it. Our next speaker is Professor Kostas Doris. He's a fellow at NXP Semiconductors and also part-time professor at the Electrical Engineering Department here in Eindhoven. He's the R&D Development Manager at the NXP Business Unit for Automotive, working with his team on automotive radar. Today we're going to be hearing a little bit more on the relevance of terahertz frequencies, again for industrial applications. Okay. Okay. We're delayed by the switching speed for Zoom. And I can take this opportunity to give you a bit more insight into what is happening next. So after the final presentation, we'll bring together a panel to discuss opportunities and applications of terahertz technologies. So for our colleagues out online audience. Oh, okay, all right, okay. So we can switch over our agenda over to the panel discussions. I would like to welcome back on a house camp, together with Dr. Nickel, VP Business Development at PhotonFest, and also Paul Merkers, who's the Head of Research Support Office here at TUE. Please welcome to the stage. So while our colleagues get up onto the stage, we're looking forward to an exciting discussion chaired by On a House Camp.
Excuse me?
I'll let you kick off the discussions.
Practical joke.
Now we are we're present here today for the launch of a new research center. And as Anna very well knows, I've also been very much involved in building out the ecosystem of the greater ecosystem of photonics. So one of the questions that ponders me, although I've been taking pictures of some of the presentations made today, is how is this center going to contribute to this ecosystem? And what role would the various actors play? I do have some answers, but I'm also curious to hear what you guys are thinking about that.
Yeah, that's very interesting. I think that today is a very important day for all of us, as Terahertz will bring, I hope, answer for the many questions and solution for society. And as we saw, this place is very well established on the map of the Europe. People who see the impact on the society know about the terahertz technology. But I think that still is quite a lot to do to make this fascinating technology more famous and indeed connected with another enabled technology like photonics, like quantum. And I'm very happy that TUE's example of the university, which thinking indeed in the center, and they, I hope, connected this in the future. So yeah, I'm very excited and looking forward. As a representative of the industry, I see a lot of calling for the action from everybody who are in the stage or online. And I think that this is the place where industry should step in to the game.
Yes, thank you. I couldn't agree more. I think Terahertz technology is the new kid on the block and very welcome to add to the spectrum of technologies that there already are, like photonics, like nanotechnology, like quantum. It's getting crowded, you could say. But on the other hand, I also think that there is still an empty space to be filled and that this nicely connects the world of quantum with the world of nano, with the world of 5, 6, whatever G there is, and that the gap is being filled and the bridge is built, and it's our challenge to position it well and to explain it. But I think the TU has proven before, like with photonics and others, that we are capable of putting something on the map. And I'm happy to hear that the province Noord-Brabant already adopted the Terahertz technology as a key enabling technology from your perspective.
Well, it's certainly encompassed in
that's
the greater...
promising first step, I would say.
Yeah. As a new kid on the technology block, as you explained it, mind you, I've been in this particular path a long time ago with the Institute of Photonic Integration. I think starting out about 7 or 8 years ago already. Back then, there was still one of the tasks that we took upon ourselves was to explain what this new technology could do. To give you an idea, in the very beginning, the only reason I knew of it was that I read on the website of the TUE that there was this center about photonics. I didn't know anything about it, and I took it upon myself to ring up one of the professors. He sadly isn't here anymore, but he explained to me, and his explanation helped convert me to help the center build out. Is it also because this is a new technology? Like I said in my speech, I don't know what is possible yet. Do you think that there is also what you could call missionary work to be done? So speeches to be made on conferences, maybe even host a small conference yourself or workshops?
Definitely, definitely. And I think there's quite a road ahead for us all to do this missionary work. And what is possible, well, what I've also seen from the presentations, a lot is possible, and we ain't seen nothing yet. So there's also this chicken and egg problem that as the technology evolves, more will be possible. And there is quite a variety of application domains, as was also shown. So there are many speeches to be held to address many application domains to see that, hey, this is an additive, additional technology that adds to societal value.
Yeah, I think that Anna brings very important point. That let's talk about this technology in the application way, something what society and the end user and we as an industry can understand. It's very important. So it's don't forget to bring to the table the province house, the all stakeholders from the triplet helix, but also beyond, also society. And I think that speaking about the application is something what really bringing this call to action in the move. Yeah, because that's what's working. Because looking for the presentation which we saw, I immediately saw connection with my company and where we can use this technology and bringing further to the end customer. So that's very important. So keep the good work and preach about this terahertz application. I think that's important. Yeah.
Now there's one other question. Again, as a non-technology person on the stage in this case, what would be the killer application for terahertz technology? Is that in the healthcare domain, in the communication? Personally, I wouldn't know, but if
that's very interesting. And I was we saw some application. I was also got a briefing about the center, what the guys you are doing, and some of the application are fascinating. So for me, this alternative of the more safe X-ray and beginning from 2 analysis to the measure the cancer tissue which we saw in the brain, or also even measure what what kind of the hemoglobin is in the tissue. That's amazing. Another example which I personally find very important is checking the pharmaceutical and medicine quality, yeah? If they have the active substance or not. I think that the World Health Organization assumed that 150,000 people per year die using the fake or contaminated drugs, and this is $200 billion market even before Corona. So that's, I think that it's a very beautiful example where terahertz can be used. Yeah.
Yeah, it may be the time now to make bets. What will be the killer application? And the future is typically hard to predict, so we don't know yet. I think this is fundamental research, is emerging into more application-oriented research, but it's still research. I hope that thanks to the public-private collaborations that we will make, it will advance further into application, and we will see what the winner will be. I think it's too early to say now, but I'm also longing for that idea to say what will be the killer app that draws it all. I would expect in healthcare, the cure for cancer is what we all need in general, and this could contribute. So that for sure has a great value. But as there are so many possible applications, it could be otherwise. It could be something that we all do not think of right now, that will surprise us.
Wow. That poses a challenge in finding the right compelling story.
I think it is a key enabling technology. It's key, it's technology, but what will it enable? Well, it will enable a lot. And that will all have a certain value, and some will have more value than the other, and one with the most value will be the killer app that will give a pull to the whole process.
The main reason I mentioned it, and maybe I'll end it with that, as I see Chigo already moving on stage.
He's there.
The reason I mentioned it is that, and perhaps, again, this is maybe a bit premature, given that we're seeing the birth of a new research center, so it's premature to talk about scaling it up. But once you start thinking about scaling up, you need a compelling use case to keep it in the mind of the politicians and the civil servants that you will undoubtedly need to get the larger type of funding for scaling.
And industrial partner.
That too.
Yeah.
In the end, for photonics, the main use case they presented themselves with was communications. And they basically said the world is going to end in a couple of years if we don't build better chips, and we can provide them. And well, we all know what happened after that. I'd be interested to hear and see what the case is going to be for Terahertz technology. But I think
the super eyes will show us things that we do not see now. And what will they be?
Who knows?
Who knows?
Thank you very much. With this, I would like to thank Anna Hauskamp for joining the panel, Anna Nicol, and Paul Merkers.
Yes.
Really appreciate your participation. Thank you very much.
Okay, thank you.
So thank you everybody out there in the audience and also here live with us. The panel discussion has really shown a real interest and exciting opportunities of Terahertz Science and Technology. There will be a second Dutch Terahertz workshop on the 27th of January. If you would like to be on the mailing list, please email us at ctste@tue.nl. So with this, I would like to formally close the ceremony. It has been my pleasure to act as your master of ceremony. Those present here, please join us for coffee, tea, and sandwiches in the auditorium hall. So for those of you following us online, we hope to see you soon, and we hope that the exciting presentations and pitches that you heard today triggers collaboration for the new Center of Terahertz Science and Technology in Eindhoven. Thank you very much.